All right, should I get started? Okay. So I wrote down some of the, on the top board, some of the equations. Is this working? Maybe I can just put it closer. Some of the equations that I wrote on the board in the morning. In particular, one of them that's going to be important is that for identical scalar primaries, the 4-point function takes this form. I didn't write what u and v are, so u is x12 squared, x34 squared, over x13 squared, x24 squared, and v is x14 squared, x23 squared, over x13 squared, x24 squared. V is obtained from u by interchanging 1 and 3. And then this 4-point function satisfies crossing equations. And the first one is obtained from interchanging 1 and 2. And this one is obtained from interchanging 1 and 3. And where we left off is that the reality conditions, the conjugation relations in radial quantization. So if we interpret the logarithm of the radial distance as the Euclidean time that we're going to continue to the Lorentzian time, that imposes, so if then the Lorentzian theory is unitary, that imposes some reality conditions. And in Euclidean signature, if we go back to Euclidean signature, then O of x dagger takes this form, if O has dimension delta. Okay? And from this, one can obtain various constraints that conformal field theories, unitary conformal field theories, should obey. In particular, if we look at the 2-point function of O, so O of x with O of x conjugate, this should be positive because it's just a norm of a state. And this condition, if you work through it, implies that for real operators, if O of x, O of y has this form, c over x minus y to the 2 delta, then c must be positive. To show that, just take, so plug in the formula for O of x dagger. And then if we impose the condition that this 2-point function is positive, so the 2-point function of p mu, the momentum operator, acting on O, and its conjugate, and this is positive, then that implies that for L bigger than 0, so not for this, we get some information not for scalars, but for operators with spin. The condition is that the scaling dimension is bounded from below by the spin plus the spacetime dimension minus 2. So in particular, in 3 dimensions, this would be L plus 1. So all operators with spin that are primaries, delta is the delta of the primary, delta O. So, so this first bound is for scalars. But the similar bound holds for operators with spin. And here I'm assuming that the operator O has scaling dimension delta and spin L, and this condition implies that delta is bigger than L plus D minus 2. Okay? Can look at this other condition where we have 2 p's acting on O, and the 2-point function is positive. From this one, we get a condition for L equals 0, namely that delta is bigger than D minus 2 over 2. Or that delta equals 0. This corresponds to the identity operator. But all other operators should obey, all other scalar primaries should obey delta is bigger than D minus 2 over 2. And this bound is saturated by free scalar fields. If we plug in D equals 3, we get that this is a half. If delta equals a half, we have a free scalar field. If delta is bigger than a half, we don't. We just have some scalar operator. Assume people have seen unitarity bounds before? Yeah.
Does the second one give you another constraint of L's greater than 0, or is the first?
No, it doesn't. It's just this constraint.
Okay. And do more p's not do anything else?
they don't do anything else. So these are the ones that give you non-trivial constraints. Well, you can ask what happens if O was a spinner, but that's a different story. I'm not going to mention. In that case, too, L equals a half is different from a larger L. Okay. Good. So another piece of knowledge about CFT basics is about the OPE. The OPE is just like a Taylor series. So I can take two operators, OI at x1, OJ at x2. For simplicity, we can assume they're scalars. And we can try to approximate this as an infinite sum over operators at x2. So the OPE in a conformal field theory is the following. So we can just sum over primaries. We have some functions of position that depend on the operators, I, J, K, A. I'll explain what A is in a second. This depends on x1 minus x2 and the derivative with respect to x2. Acting on operators OK with some index A, again, at x2. So in general, in a theory that's not conformal, we can take a product of two operators and expand it in terms of all other operators in the theory at x2. In a conformal field theory, all the operators at x2 that belong to the same conformal multiplet have related coefficients. So that's the reason why here I'm summing only over primaries, and this may be a complicated function of x1 minus x2 and the derivative with respect to x2. When the derivative acts on this operator, we get a descendant. What is A? A is a Lorentz index. Well, it's an index of the Lorentz representation. Okay? So in particular, some of these operators are scalars, some of them are vectors, some of them are traceless symmetric tensors, some of them have higher spin. So this A is just a generic name for the space-time indices. So A would be mu1 through mu L symmetrized and the trace is removed if this were a spin L operator. Okay? And this is an identity that can be used in correlation functions. So that's how we should think about it. And in order to motivate it, I can draw a picture. So let's think about having two operators here, O1 and O2. And suppose we can surround them by a sphere. And all other operators in our correlation function are outside. Okay? So in a path integral language, you can think of this as doing some path integral with some operator insertions. Okay? The idea of the OPE is that we can replace this by this sum over OK here. With these coefficients. And we keep the operators outside fixed. And the idea is that this is an equality in this correlation function. Okay? The way to think about it is in the following way. Suppose we have a path integral to describe this theory. And we do the path integral everywhere inside this ball with some boundary conditions. The answer is going to depend on the boundary conditions. So we're going to get a functional of the boundary conditions. The idea is that in here, if we were to do the exact same integral over the inside, but now with this operator insertion, for fixed boundary conditions, we're going to get a functional of the boundary conditions. The idea of the OPE is that these two functionals are the same. Okay? So in other words, the state on the sphere is the same in both cases. And then in order to compute the full correlation function, we should do the path integral outside of the sphere with the same boundary conditions, well, with some boundary conditions, and then weigh the answer by the wave functional that we got from doing the path integral on the inside. Does that make sense? So in a conformal field theory, we expect that the OPE converges whenever we can surround these operators by a sphere such that all the other operators in the correlation functions are outside of that sphere. I guess I'm not proving any convergence properties. And there's one more thing to be said about this, is that this function, or this operator,Cijka, is doesn't depend on much. SoCijka is Fijk multiplied by some function that depends only on the scaling dimensions and the spins. So delta I, Li, delta J, Lj, delta K, Lk of x1 minus x2, derivative with respect to x2. Okay. So it only, and where Fijk is the OP coefficient, so OI, OJ, OK is proportional to Fijk. Is this fact familiar to people? Yes? So this function here,Cijk, is determined by group theory only up to an overall coefficient. And that overall coefficient is the same coefficient that appears in the 3-point function. To prove this, just use the OPE in the 3-point function. And that actually gives you a formula for what this C is. Should I do that? Someone said no, so unless someone else says yes. Okay, good. So think about a 3-point function when these are just scalars. Maybe I can just write it here. So when these are scalars, we have OI, OJ, OK is equal to, this is the exact formula. So this would be at x1, this would be at x2, this would be at x3. Fijk divided by x12 to the power delta I plus delta J minus delta K, x23, delta J plus delta K minus delta I, x13, delta I plus delta K minus delta J. So this should equal, so this is OI, OJ, OK. And now we can just use that formula, the OPE, and the only term that's going to contribute of that, from that sum is going to be the term that has OK equal to the OK that I have here. So this givesCijk of x1 minus x2, derivative with respect to x2. So I'm just replacing it here. I'm replacing this by a sum overCijk, OK, at x2. And I then, if I make this replacement, I just have to compute a 2-point function. And the 2-point function would just be, if I normalize them so that the 2-point function is just 1 over the difference in the coordinates to the power y is the scaling dimension. This is x23 to the power 2 delta OK. Okay? So this is the formula for C. We have, on the left-hand side, we have a very explicit function. It's proportional to Fijk. On the right-hand side, we also have a very explicit function. Well, it's some operator acting on this, right? So how do we extract what this operator is? Well, we just expand the left-hand side when x1 is close to x2. This thing is easy, it stays the same, but in here we can replace this x1 by x2 and then start expanding, and we can recover what this function is. The point of it is that Cijk is proportional to Fijk. But it does depend on all the scaling dimensions and all the spins. Here I did it only for scalars. You can repeat this exercise for OKs that have spin. And what you'll see is that the Cijk depends on the scaling dimensions because they appear in this formula, and the spins because the formula will be different if the operators had spin. Is this clear? Okay. Good. So that's the OP. Now, how about conformal blocks? Suppose we have identical scalars. So let's just do an example. Let's just call, if they're scalars, let's just call them phi. I know I called them O before, but now let's call them phi. 5x1 through 5x4. Oh, maybe I actually want to write it. 5x2, 5x3, 5x4. So the idea of conformal blocks is that we can just replace the product of pairs of operators by that infinite sum. So let's say we do it for these two and then for these two. So what do we get? We get a sum over OK and OK prime. OK from this guy, OK prime from this guy. And we have, so I'm just going to use this expression over here. They're proportional to the OPE coefficients, to the 3-point function coefficients. So this is phi OK, F phi OK prime times C A of x12 derivative respect to x2, CB x34 derivative respect to x4 multiplied by the 2-point function OK of x2, OK prime of x4. So this is A and this is B. Again, A and B stand for these Lorentz indices, so A stands for a multi-index, just mu1 through mu-L, symmetrized and with the traces removed. This 2-point function is non-zero if we choose our basis of operators right, only if OK prime is the same as OK. So this double sum collapses to a single sum. This is then sum only over OK, F phi OK squared multiplied by CA of x12 derivative with respect to x2, CB x34 derivative with respect to x4 multiplied by this 2-point function. So 1 over x24 to some power 2 delta OK times something that depends on A and B. That also depends on x2 and x4, x2 minus x4. Okay? So this is the conformal block decomposition. Of course, the 4-point function we said before is 1 over x12 to the 2 delta phi, x34 to the 2 delta phi, times g of u and v. So this is a complicated way of writing this. So that implies that G of U and V can be written as a sum over OK F phi phi OK squared times some function of U and V. And that function will depend on delta and L for this operator OK. So maybe I can, instead of writing the label K, I can write the label delta and L. So in other words, this thing here must be a function of U and V, and it's this thing that I'll call G of G sub delta and L. Okay, it's not so obvious from this expression. Well, I guess this is a function of U and V multiplied by this quantity over here. Okay, it's not obvious from this expression that this is the case, but it must be true because we study properties of the 4-point function. Yeah.
Does it matter how we group the phi's? Like, if we group like
it shouldn't matter. We should get the same answer. But of course, the expressions look very different. So and that's exactly what the conformal bootstrap is going to take advantage of. That there are several ways of doing this, and the several ways should give the same answer. Okay. So, in general, one thing one should remember about this is that this G of U and V, G delta L of U and V, is determined by group theory. So this is determined by group theory. Maybe I can raise this board a little bit. This is determined by group theory, but OK. So these operators, O delta L, and these constants, F phi phi O, are determined by dynamics. So in other words, for any conformal field theory we have, if it has a scalar operator, the 4-point function is going to take this form where G of V is going to can be written as an infinite sum like this, where all these G delta L of U and V are known functions of U and V. I'll explain in a bit how they're computed. Unfortunately, we don't know which deltas and L's to include in the sum, and we don't know what these F's are. Okay? So while it seems like this is a lot of progress, there's still a lot of work to do because we have to determine these things. Okay? So my understanding is that Sheehan explained the rough idea behind computing these conformal blocks. So I'll just mention what the idea is. And then I'll tell you how to do the computation. So calculate G delta L of U and V. That would be the task, the first task. Okay? And I'll just tell you what the answer is. The answer, the way to calculate it is to derive a differential equation that it obeys. So it obeys an eigenvalue problem of this form, some differential operator acting on G delta L of U and V. So this is differential operator. It's a second order differential operator in U and V. I'll write it out. Is equal to a delta times delta minus D plus L times L plus D minus 2, multiplying the same thing, G delta L of U and V. where does such a relation come from? Well, the idea is the following. Act with the Casimir of the conformal group. So this would be minus 1/2 LAB. Maybe I can, instead of writing AB, I can write alpha beta so that you don't get confused with the A's and B's that appeared before. L alpha beta acting on the first operator plus L alpha beta acting on the second operator times L alpha beta on the first operator plus, well, maybe I want to contract these indices, so I should put them up. Alpha beta acting on the first, L alpha beta acting on the second. So act with this on the 4-point function. What are these L alpha betas? Well, some of them are they're all the conformal generators. They're the rotation generators, there's a translation, special conformal transformation, dilatation. Okay. 1 means it acts on the first operator in the 4-point function, and 2, it means it acts on the second operator in the 4-point function. So if we act with this on the 4-point function, so suppose we act with this operator over here. Or maybe it's even better to think about it as acting on the OPE over here. The OPE, these are the first 2 operators. This is part of the 4-point function. Suppose we act with this operator on the OPE. What's going to, we can replace the action on these 2 operators by the action of this Casimir on this guy over here. And because the Casimir commutes with all the generators of the conformal group, what we're going to get when we act with the Casimir on this operator, we're going to get the eigenvalue corresponding to this representation. So this is just a representation theory argument, and that eigenvalue is given by this. So this is the eigenvalue for the representation starting with delta and L. So delta and L is the conformal primary, and then in this representation they're also descendants obtained by acting with P mu. And on any of these, if we act with this operator, we're going to get that value because this operator is the Casimir. Did she explain this? Sort of. Is this better? No, I didn't mean to write that. Is this clear? Okay. So anyway. So far so good, but don't leave things out. Okay. So anyway, there's a way of determining a differential equation for these conformal blocks. So I should tell you what the differential equation is and then how to solve it. To write the differential operator, it's useful to, well, people usually write it in a different set of coordinates, not u and v. So useful coordinates. I really apologize about this, but this is what people do. So they write u as z times z bar, and v as 1 minus z times 1 minus z bar for some variable z and some variable z bar. The motivation behind this is the following, is that so we have 4 operators in our 4-point function, and they're inserted at 4 positions. We can put one of them at the origin, so say x1 equals 0. We can put the third one at x equals 1, And we can put the fourth one at infinity. And we can put the second one here in a given plane. So if we act with conformal transformations on this 4-point function, we can arrange such that 3 of these points are in the configuration that I mentioned, and the other one is in a given plane, but we can't choose where in the given plane it is. Okay? And we can parameterize this plane by a complex coordinate z. These are the z is just the coordinate of this point. So this is z. The cross ratio u is, if we work through the definition, so the definition was x12 squared, x34 squared, divided by x13 squared, x24 squared. Since you're taking the limit at x4 goes to infinity, that reduces to the distance between x2 and x1. So this distance is square root of u. U is the square of this distance. And if you work through the definition for v, it's this distance. So square root of v is the distance between x2 and x3. Okay? And in these coordinates, this is just so I can write down the differential operator. So this is, just so that it's concrete, 2 times z squared, 1 minus z, d by dz squared, minus z squared, dz squared, plus the same thing with z interchange with z bar, plus 4 times d minus 2 divided by 2, z bar, z minus z bar, 1 minus z, dz, minus 1 minus z bar, d by dz bar. Okay. So these conformal blocks are functions of u and v that obey this differential equation. You can see that here this term just involves z, and this term here just involves z bar. But this last term mixes them. So they're non-trivial functions of z and z bar. The mixing disappears when the spacetime dimension is equal to 2. And in that case, the conformal blocks are just products of some function of z and some function of z bar. But in general, that's not the case. Yeah?
What's the plot you were writing? Yeah.
x1, 0 should be clear. That's the origin. 1, 0, 0, 0. Infinity should also be clear. And this is, say, in the first 2 coordinates. So the coordinates of this point would be, I don't know, real part of z, imaginary part of z, 0, 0. Yeah, okay, good, thank you. Okay. So to solve this, okay, so this differential equation doesn't have closed form solutions in odd spacetime dimensions. It does in even spacetime dimensions. They're hypergeometric functions. So the question is, what do we do in odd spacetime dimensions? Because we're, as I was saying in this lecture series, we're doing d equals 3, which is odd. So to solve this, to solve this equation star, which is this equation, I'd like to introduce, unfortunately, another set of coordinates by taking the 4 points in a different configuration. So let me still take them to be in a plane. And I'll take one of them here, one of them here, one of them here, and one of them here. So this is x3 equals 1. This means 1, 0, 0, 0, 0. x4 equals minus 1, minus 1, 0, 0, 0, 0, 0. And this is x2, and this is x1. And this distance is r, and this angle is theta. So the new coordinates are r and theta. And I can try to write down u and v in terms of r and theta, but the formulas are pretty complicated. But it's just a change of variables. Okay? And these are particularly convenient coordinates because in these coordinates one can develop a series expansion, a simple series expansion of this function g of delta L of u and v, or of r and theta. And it looks like this. So you can take this as an ansatz. It works. You can plug it in the equation and see that it works. So r to the delta multiplied by Legendre polynomial of cosine theta plus r squared times some function of theta plus r to the fourth times some function of theta, some other function of theta, and so on. And this is just a series solution to the differential equation. You try to take this ansatz, so it's a series expansion in R, take this ansatz, plug it into the differential equation, and solve for the functions f1, f2, and so on, order by order. Okay? So that's the procedure. In practice, we should think of these g's as known functions. Using Mathematica, we can compute them to however many orders in R we want. In practice, it's good to compute them up to 40 orders, 50, 60. Okay? So these are the Legendre polynomials in 3D, and general dimensions, these would be the Gegenbauer polynomials. Okay. So I want to make some comments about this. Well, maybe just several comments. Let me start with explaining why there is an r to the delta. So why do we start? It's a series expansion in R, but how do we know where to start? Why don't we start at r to some other power? So let me try to explain the r to the delta. So if we take this 4-point function, well, maybe before I do that, so this is an expansion at r, at small r. At small r, x12 is very small. So that means that small r means small u, or x1 is close to x2. And for the purposes of explaining this, let me also take x3 close to x4. So this is approximately, so if x1 is close to x2 and x3 is close to x4, then we take this OPE and we replace this by some operator of dimension delta and L, and we do the same thing here. And then how is the coefficient of this operator going to behave? So I'm gonna need to have something involving a 2-point function O delta L at x2 and O delta L at x4. And the question is, how is this coefficient going to depend on x1 minus x2? Well, it's going to depend on it in such a way that it's consistent with the scaling dimensions. So this would be here 1 over x12 to the 2 delta phi minus delta O. And here we're going to have x34 to the 2 delta phi minus delta O again. And if we calculate the 4-point function, so this will look like, from here we get, well, okay, let me write it. So let me write this like this. x12 to the delta O, x34 to the delta O, over x12 to the power 2 delta phi, and x34 to the power 2 delta phi, and from these two we get a 1 over x24 to the power, maybe this is kind of not, let's write it like this, So x24 to the power minus 2 delta O from that 2-point function. Now, we took the limit where x1 was close to x2 and x3 was close to x4. So if we're just doing approximations, we can replace this x24 by x24 squared by x24 times x13, because they're about the same thing. And after we do that, we can recognize that this product in the numerator is just u to the power delta O. So this is approximately u to the power delta O. I'm sorry, delta O over 2 divided by x12 to the 2 delta phi, x34 to the 2 delta phi. And if you trace back to the definition of R from U, I didn't write it, but you can try to think about what U is when R is very small. You get that U is approximately 16R squared. So I can try to write here. So U is approximately 16R squared. So then this whole thing goes like R to the power delta O divided by x12 to the 2 delta phi, x34 to the 2 delta phi. Okay, good. So that explains the power of R, where we start. Okay. So let me try to make a few brief comments and then get to the Bootstrap idea. So, comments? The first comment is about the normalization. So, O delta L is proportional in general to some constant CO divided by x to the 2 delta. Now, we define these f's as like this. The 3-point function phi phi O was proportional to f phi phi O times some function of position. So that means that if we think about the OPE, the phi phi OPE, O appears in that OPE, but the coefficient is f phi phi O divided by CO, because we should get this 3-point function if we take the 3-point function between phi phi and O, then from this 2-point function between O and O, we get a CO. So then if we write it like this, then we'll reproduce the left-hand side. Okay? That means that the 4-point function, phi 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 phi, if we do this OPE and that OPE, we're going to get, I'm just going to keep track about how keep track of how O appears. So we're going to get from this thing, we're going to get an f phi phi O over CO. From this other guy, we're going to get the same thing squared, and then from the 2-point function of O, we're going to get a CO. So this is like f phi phi O squared over CO. The reason why I'm saying this is the following. So I'm just going to write it here. So if we fix the normalization of G delta L, if we define f as in the 3-point function here, and if we require that G of U and V is sum of f phi phi O squared times G delta L. That implies CO is determinate. What I'm trying to say is how many independent things we can fix. If we want to have the f's defined by the 3-point function, and we want the same f's to appear in the 4-point function with no additional coefficients given some normalization of G, that means that we have in mind some normalization of these operators O. If, on the other hand, we fix the normalization of the operators O, and we define the f's by the 3-point function, then it would no longer be true that the G is sum of f squared times G delta L. It would have to be divided by some number CO. Okay? So, when people say that by unitarity, unitary theory, this thing is positive, there's something behind that, which is that this thing here is not positive solely because it's the square of a real number. It's also because what it really is this OP coefficient defined by the 3-point function divided by CO, and CO is also positive. Okay. Maybe that comment was too detailed. So another comment that I want to make is examples of operators. We're always going to have the identity operator. So that has delta equals L equals 0. So the operator O is the identity. This block G00 of, so G had the indices delta and L of U and V. In this case, it's very simple. It's also equal to 1. And this corresponds to the disconnected part of the 4-point function. So phi, 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 phi. The identity appears when we just contract these two. When we write this, so this would be the disconnected part plus other things. And we can think about the disconnected part as corresponding to the identity operator appearing in the OP of phi and phi. And another operator that I want to point out is delta equal 3, L equal 2. And this is the stress tensor. It appears in all local conformal field theories. That's the definition of a local conformal field theory, is theory with a stress tensor. And in general, we don't know other deltas and L's. And the last comment that I want to make about this is that if we have identical external operators, then only operators with even spin can appear. So identical external scalars implies that only operators with even spin appear in the intermediate channel. Another way of saying it is that f phi phi O is equal to 0 if L is odd. The reason why this is true is we can just look at the 3-point function phi of x1, phi of x2, O delta L. It's got some indices at x3. And we can write down what this 3-point function is. It's complicated, not easy. But this is anti-symmetric under x1. Well, go into x2 if L is odd. and it's symmetric if L is even. You can just write down the explicit 3-point function and convince yourself that this is true. So that implies that, of course, the left-hand side is symmetric under interchanging x1 and x2. So that implies that f is 0 if L is odd, so that means that only even spin operators appear. By the way, the picture for this conformal block decomposition is this. You can just think about it like that. So this is the first F, and this is the second F. But it's just a picture. Okay. And the Bootstrap idea is that, well, it just combines all these elements. So we have the conformal block decomposition, and we also have the fact that the 4-point function obeys these crossing relations. So recall that g of u and v was u over v to the delta phi, the dimension of the external operator, times g of v and u. By the way, there's another relation that I wrote down that relates g of u and v to g of u over v and 1 over v. That's automatically satisfied by all the conformal blocks of even spin. So we don't have to consider, the only non-trivial one is this one. Okay? So we can just rewrite this. So rewrite as f. Let's just define some function capital F of u and v, which is by definition v to the delta phi g of u and v minus u to the delta phi g of v and u. And the crossing equation says that this should be 0. And can combine this with g of u and v, the sum of over O of f phi phi O squared g of delta n L u v. And the combination gives another equation. I have until 5, right? Okay. Okay, so let me just write down the combined equation. The combined equation is, so I'm just going to plug that in there, and I'm going to take the sum outside. So have f phi phi O squared v delta phi g delta L of u and v minus u to the delta phi g delta L of v and u is equal to 0. So I can just call this function here that appears capital F of delta L of u and v. Okay, so this function is determined by group theory. Just because the little g's were determined by group theory, we don't know the little f's. But we know that they're positive. Remember the comment that I made before. In a unitary theory, they're positive. Okay? And let me have one more rewriting of this, where I separate out, since the identity operator always appears, let me just separate it out. So let me, and the OP coefficient, I can set the OP coefficient to 1. So let me write this. So this is the contribution from the identity operator, and assume f phi phi 1 is equal to 1. That's just a normalization condition for the external operators. We can always assume that. Plus sum O delta L F phi phi O squared F delta L of U and V is equal to 0. And this is an equation. Well, it's not just one equation. It's an infinite number of equations because this has to hold for all U and V. And the conformal bootstrap idea is that it's possible to rule out certain assumptions about the spectrum. So suppose that we know that some operators, some deltas in L appear in the theory. Well, suppose that those are the only ones, the ones that we know. And if we can find a set of U and V, for instance, such that all the terms here are positive, and this is also strictly bigger than 0, then we know that this equation cannot be true. Okay. More generally, maybe, evaluating this equation at a specific point would not be enough. We have to combine it, evaluate it at different points. And maybe we can find an instance, you find a way to prove that this equation cannot be satisfied for the spectrum of operators that we assume. So let me just give an example. So the idea, rule out assumptions about the spectrum of operators. So here's an example. Assume we have a CFT with some scalar primary phi, and assume that all other scalars, so all scalars in phi OP have delta bigger than some value delta star. And we don't have to make any other assumptions about this theory. So then the claim is as follows. Maybe I can write it here so that it's higher. So let me first define a linear functional. So I'm going to use a linear functional alpha. What is alpha? What is a linear functional? A linear functional is a function that takes as input a function of U and V, and it outputs a number. In particular, I'd like to act with a linear functional on this equation. Because it's linear, for instance, when it acts on this product, this f squared goes up front. So the claim is the following. If we can find alpha, it doesn't matter how we construct it, a linear function, such that alpha, when acting on the first term in the sum, on f00, so this returns a number. So suppose the number is 1. This is how we normalize our functional. And alpha on all operators with spin 0, so delta and 0, is bigger than 0 if delta is bigger than delta star, which is our assumption about the spectrum. And if, moreover, for the other spins, f of delta and L is bigger than 0 if delta is bigger than the unitarity bound, which in this case is L plus 1, if L is bigger than 0. So we can find, if we can find an alpha that satisfies these properties, that means that that equation cannot be true. So let me call this equation box. So that means that the equation box is false. It cannot find any f such that that equation is true, regardless of the value of f5 phi o. So the conclusion then is that one of the assumptions is wrong. Well, this assumption is just a normalization condition. This assumption doesn't involve, doesn't make any assumptions. It's not an assumption. So that means that this assumption is false. So that means that there must exist an operator with a scalar operator with delta smaller than delta star. So this way we get a bound, an upper bound, on the lowest singlet operator. Sorry, the lowest scalar operator. And if we, well, people did this and made the plot. So I'll just copy the plot on the board. So the plot is this. So this is upper bound on the lowest dimension scalar and the phi OP. And I'm gonna make that. I'm gonna draw this bound as a function of delta phi. So this is an upper bound. It starts over here. At that point, I take it to be 1/2, 1. So when delta phi is 1/2, and the dimension of this scalar is 1, and the bound looks like this, where the coordinates of this point are approximately 0.518 and 1.41. Okay, so maybe I should write down who did this. So El Shok, Paulos, Poland, Richkov. Now that I started writing them, I have to write all of them. Simmons Duffin and Wiki. I should have said El Shok et al. Okay, so you might recognize these numbers from the lecture on Friday. They are the scaling dimensions for the CFT that's supposed to describe the critical point of uniaxial magnets, or of the water vapor critical point, or of the Ising model. This is a 3D Ising model. And the idea is that, I guess the sort of intuition behind this is that, you know, there aren't that many CFTs, maybe. And these constraints, the constraint coming from crossing and unitarity, are very strong. You know, as we increase the precision of the numerics, I mean, this is of course done all numerically. As we increase the precision of the numerics, then the bound comes down and sort of gets stuck at this point, because that's where an actual theory is. Yeah. What's the? Good. Yeah. Let me. I'll say that. Good. Okay. So this is the plot. Now I can tell you how it's derived. The alpha that's used is of this form, right? So alpha f, function of u and v, you can think of it as a function of z and z bar. It's a sum n and m from 0 to some n max. some coefficients, alpha n comma m. These are numbers. And this is the derivative with respect to z of order n, derivative with respect to z bar of order m, acting on this function of z and z bar, evaluated as z equals z bar equals a half. Well, z equals z bar equals a half is a special point. Well, it's one of some special points. This is a set of special points. At this point, if z equals z bar equals a half, if you remember the definitions of u and v, so u was z bar, v is 1 minus z, 1 minus z bar. So at this point, u equals v. So this implies u equals v equals a quarter. So crossing is particularly simple here because crossing interchanges u and v up to some overall factor. But if you take u and v to be the same, then it's easier to study the equations at that point. And of course, this parameter n max is some parameter that you can use, and you can try to increase it to search for over a larger space of functionals, and alpha and m are just numbers. And okay, so then the problem is to find a functional that satisfies all of these conditions. So, you can use that expression and try to search over all the possible values of alpha and m until you find a functional obeying this condition. This can be phrased, this is something I'm not going to explain. So finding alpha can be phrased as a semi-definite programming problem. And there's a software that David Simmons-Duffin wrote. It's called SDPB. So this is David Simmons-Duffin. And this is in practice what people use to do this. This software comes with a paper on archive that you can read if you're interested in implementing this thing numerically. Okay? Other questions? Yeah.
So is this alpha unique which gets this?
No. There's many that do. Well, it depends on where. Over here, in this region where we can find alpha, we can find many alphas. As we go closer and closer to this boundary, it's harder and harder to find alphas. Well, because when we cross this boundary, we're not going to be able to find any. Okay? And the idea is that, alpha in itself doesn't have much meaning, except for the zeros of alpha. So what you expect as you get closer to this bound, the zeros of alpha acting on f. So alpha acting on f of delta and L. So for instance, for fixed L, if I plot it as a function of delta, it would sort of look like that. Because if I then, as I get close to this boundary, if I go past this boundary, then some of these things are going to start being negative. So it no longer obey the condition that is positive. So the zeros of alpha correspond to, from the zeros of alpha, one can extract the dimensions of actual operators in the theory if the theory saturates this bound. So there's some information in alpha, but not a lot of information. Well, the scaling dimensions of the operators is a lot of information. Okay, are there any other questions? Yeah. Mm-hmm.
But so, should it be only if you're not zero because you're zero so right, you can pass like
Right. Okay. Good. Good. It's true for infinitely many values of
you can
UNV.
also like insert like a filter.
Right. Right. It's true for infinitely many values of UNV. Okay. Maybe I should say one more thing about this because this is actually important. I explained how to construct the conformal blocks as a series expansion in R. Now, that's an expansion around U equals 0. Now I'm saying that, well, okay, in order to construct this function, you should evaluate the conformal blocks at U equals V equals a quarter. What value of R is that? Is that a small enough value of R such that the series expansion in R is good? And the answer is yes. So this is R approximately 0.17. It's some irrational number. And 0.17 is small enough so that the conformal blocks converge. Now, if you go to very small u, what's going to happen is that the conformal block, so if you go to very small u, then this is going to converge very well, but this isn't going to converge very well. So there's also that limitation. Maybe, okay, I should say holds for infinitely many UNV. Okay, all I wanted to say is that this is an infinite number of equations, not just one equation. Yes?
So I'm looking at your curve with the cusp on it there.
Yeah.
So presumably the cusp is coming as I take, say, the sum to some very, very large number of terms.
Yeah.
Okay. So if I do something in low order, I would have something hard above the thing.
Absolutely.
As high as you can go, and it's wrapped itself around this point.
Yeah, that's correct.
Makes pictures where, so,
Yeah.
so that's a bound in one direction.
Yeah.
I've seen people beating up on people with Monte Carlo with little boxes.
That's right.
Is that far?
That would be
You know, I
for.
know that
Yeah, well, maybe it's for. I can even say it now if I have like 3 minutes, 4 minutes. I can say now. So this is what one gets from studying a single 4-point function. But one can study a system of 4-point functions, not just one, but maybe a few. So if one studies the system where we have, so let's just study CFTs with two scalar operators, scalar primaries. Let's just call them sigma and epsilon. And the Z2 symmetry, where this is Z2 odd and this is Z2 even. And then we can do a similar thing, but a little more complicated, for a system of correlators. Sigma, 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 epsilon, sigma, epsilon, sigma, sigma, epsilon, epsilon, and epsilon, 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 epsilon. And it gets pretty complicated. Then, if you do the same plot, have delta sigma on the x-axis and delta epsilon on the y-axis. So by the way, maybe I should say that in the sigma sigma OB, we have Z2 even operators. For instance, epsilon is one of them. Example, epsilon. In the epsilon epsilon OP, that's the same. In the sigma epsilon OP, we have Z2 odd operators. Example as sigma. And with the same conditions as before, one obtains the same plot, like that. However, So this is the same as the single correlator of the sigmas. However, if one makes an additional assumption, so additional assumption is that sigma and epsilon are the only relevant scalars. How does one make that assumption? One makes that assumption by requiring that alpha of f and delta and 0, 0 for scalars is bigger than 0. For instance, if delta is delta sigma, so for Z2 odd operators, if delta is delta sigma, or if delta is bigger than 3. So we impose fewer restrictions on finding alpha, so it would be easier to find alpha. And similarly for epsilon. So alpha, so for Z2 even sector, it's a similar condition with delta epsilon instead of delta sigma. Then what happens is that the allowed region is just a very tiny island around this point. So the allowed region reduces to that. And well, it's not just this. There's also a bigger allowed region on this side. Okay, but there's an isolated island. So this would be the allowed region. And indeed, the size of the island is smaller than Monte Carlo results. Maybe I should say who did this, because this is really impressive. Coase, Poland, Simmons-Duffin, and VT. Okay, so my plan for tomorrow is to show you a couple other examples where one can find these kinks that look very similar, and hopefully in all of those examples one can eventually find islands, and then explain what else one can do using similar ideas, and maybe I'll also mention when we can actually compute these OB coefficients, supersymmetric theories, and how. Okay.
If I take a 5-point function,